Hello, and today I want to demonstrate a circuit which can model the trajectory of a bouncing ball. Now, the analog computer boards are assembled. There's 3 identical boards. Each one, let's zoom out in on one here. Each one, like this one here, can perform one integration with this chip and this network of components, and one summation with this network here. You can change the capacitor of this switch to change the rate. You can change the element and feedback with the summation amplifier here. This sets the initial condition, and these are the inputs for the integrator, input for the summation amplifier. The output for both is here. The power is also routed here, but these boards interconnect, so this one powers this one through these D connectors here and here. Again, the same lab grade power supply was used right here, and this board is just a temporary patch panel, if you will, with the potentiometers, which are the coefficients in use in the system. Now, how it works, and it's rather convoluted. You have it's integrating the gravity coefficient twice with 2 integrators, and then it's using a series of summations and scalar constants and a precision clamp to take into account the ball's effect of hitting the ground. And so you have this equation: acceleration d squared p dt squared is going to equal plus g plus this term here, which is the drag term, and this term here, which is the rebound term. And what happens is, again, E is a constant, K is the spring constant, E is the damping constant, K is the spring constant, G is the gain, or how much energy is gained or lost when it hits the ground, and M is mass. And this is the flow chart. Again, this was based on the Heathkit AC1, which was a common educational analog computer back in the day. And actually, the inspiration for this project, again, nuts and bolts, it's their trademark, I'm just using it to reference here, but the inspiration was this project in the May 2016 article, the restoration of a Heathkit EC1, a brilliant machine. Here is the original schematic if you want to freeze frame. I'm sorry I've drawn over it, but what it would do is it would model a bouncing ball effectively. And I've only built just the kinematic part. These elements here draw the figure as on this page. You can see it's the model of the bouncing ball. Again, this is the complete apparatus, which the author of this article, a man by the name of his name's not here, David Goodsell, I'm sorry, right here, wrote. And I will make a video describing the exact system. Again, I've only had limited time. This is the last day I'm at Tech for fall of 2016. And so, essentially, this network here is summing together the terms which make the drag force and the rebound force in the ball. And this precision clamp is what differentiates between when the ball is falling down as opposed to when it's going back up again. And it's this equation, which I will provide a supplement to this. I just wanted to demonstrate the system. It's kind of a mess. I'm sorry. It was patched together in an evening. And again, these 3 boards, 1, 2, and 3, were completed. And essentially, this network here is the same system as the EC1, only we're using solid-state op-amps and small modern relays. And all the components are 1%. The operational amplifiers are LF412, low noise, low offset, high bandwidth op-amp, so it's approximately the ideal op-amp, more or less. And you can see the completed board here. I'm sorry there's wires over this. if I were to disconnect it, the circuit wouldn't work. But the purpose of this video was to demonstrate the bouncing ball circuit, which is a basic problem in classical physics. And so now I'll turn on the power supply and adjust the voltage to the relays function. And I'll turn on the oscilloscope. Give me just 1 second here so we can see the output. 1 second. I'm using the MIDAC on my computer, as you can see. And again, I'll eventually use a better scope. And one of the reasons I didn't make it compute the XY trajectory is because simply I don't have an XY oscilloscope. This oscilloscope is only, again, it's a basic scope. It only does waveform versus time. So now I'll turn this on. I'll scale the time correctly this time. Excuse me. And let's wait. So now you can see there's some noise, and the initial position of the ball set on the integrator is -10 volts. So when I throw the computer on run mode, you can see it's given an initial velocity, and then it descends back to the earth, which is 0, and from there it bounces several times and then decays. Again, if you could see this on a plotter, you would see the exact same plot. And the cool thing is, we have the coefficients on this board. This one is the mass, damping factor, spring constant, coefficient of gravity, and this one is the gain, so how much is gained or lost when it hits the ground. And again, this is very rough. I eventually want to do better, but I'm a college student and my time is limited, and I thought this would be an interesting project, and it's one I've wanted to do and document, in fact, since at least May or June of this year, and actually longer, because I've seen this circuit for many years now, even before that article was published. But let's see what we can do if let's say we want to hypothetically let's adjust the damping factor a little bit. Now let's see what we can get on the scope. Zoom in real fast, and on she goes. Wait a sec. So you can see now it's losing all the energy. What if we went the opposite way and we made it so that there was no damping, and in fact the system could in principle vibrate forever? So I'm sorry, this is actually the spring constant potentiometer I'm adjusting here. Let's see what it does now. Alright. Well, you can see how it tailed off there. That's not quite enough. It had a little bit of force. Let's adjust this one upwards just a bit. Again, it's solving a discontinuous differential equation, which is, to say the least, difficult to do. Alright, no, I'm going the wrong way here. Give me a second. This one was set properly. Just give me 1 second here. But essentially, the analog computer is an effective means to model differential equations. It's not perfect in its accuracy, and its results are not perfect either. But for many things you don't need perfection, you just need it to work. And the margin of error can be non-zero. So now you can see I've adjusted the damping constant. I'm sorry I was off for a second there. Let me get out. And so now we can zoom back in. I'm sorry, my hand's shaky. I'm tired. But now you can see it takes a little bit longer to decay to 0. Just a little bit. But what happens if I adjust the damping to the point where it is not losing energy? To the point where the ball is actually gaining energy or continuously oscillating. And even though this scenario would not happen in real life. It's not beyond the computer's realm of computation. Again, I'm sorry this video is rough and first hand. I'm eventually going to make a better one. This has to be taken apart when I leave my dorm here today. It's December 16th, the last day of the semester. Okay, so now let's see what this will do. So now it's not losing any energy. Alright, 1, 2, 3. So you can see it, I mean, it's being clipped at the top. That's one of the limitations of analog computing. You see right there on the top of the waveform? It can't represent a quantity larger than a certain magnitude, and consequently it clips the top of the waveform. That would be a perfect parabola otherwise. But you can see that the system is indeed modeling. Oh, I turned it off. Let me turn it on. I'm operating this manually. You can hear the relays. You could, in theory, replace the relays with MOSFETs, enabling immediate switching. So now you can see this now as I adjust the damping. So now we're altering how much energy is being gained or lost when it impacts the ground. Let me just get my screwdriver here. Position. Okay, now watch the screen carefully. Slowly increasing the damping. And sorry, I might be turning it the wrong way. I eventually want to get vernier. Oh, there we go. So you can see it. The system died out right about there. So you can model the differential equation in real time, which is interesting. So now you can see it dies off. And again, I mentioned this one controls the mass, damping, spring constant, gravity, and the gain or loss of the system, which is related to how large the amplitude would be. The rest of this board isn't doing anything. These three are the effective analog computer. And so yes, if it had the circuits which would model the drawing of the ball, essentially solving equations that yield to sine and cosine, so the unit circle could draw the ball, then in principle you would see a bouncing ball. And this was initially on the Heath kit EC1 from 1959, and it was a science experiment that was done with that system. I hope this was interesting, and thank you for your time. Bye.